I'm Eric Anderson. I'm on the gRPC Java team. I'm the tech lead for that. I work at Google. And I'll talk some about using gRPC for long-lived and streaming RPCs. So a little bit of sort of who I hope is coming so that you get the most out of it, the talk. I hope you have used gRPC before. You don't necessarily have to have used a lot, but maybe you made a service, you made a couple clients, you sort of played with it. And then you're sort of interested in more advanced use cases. So a little bit of an overview. I'll start talking about just like long-lived RPCs and sort of some of the things regarding those. And then I'll go more into detail about streaming RPCs, and then streaming plus long-lived RPCs. So here for long-lived RPCs, that can probably mean a little different things to different people. Some people think 1 second is a really, really long RPC. I'm not too particular myself, but generally, basically, if it's lasting minutes or hours or days, that would be long. Something that's order of magnitudes more than you would normally talk about. And where it really starts crossing the lines, starts mattering for some of the issues we'll get into, like load balancing and things like that, because of how it sort of impacts other parts of the system. Some of the use cases. The main one is for something sort of resembling a hanging Git, if you've used other systems. But basically, you can start an RPC and have it just sit there waiting for some event to happen. If you weren't, and so it may last quite a while before that event actually happens. The benefit of this is like the alternative is you do an RPC, hey, has it happened yet? And it's like, no. And then you wait and you sleep a while and then you try again. So going ahead and doing a long-lived RPC reduces the total number of RPCs you do, while also as soon as the event happens, you already have an RPC outstanding, you can go ahead and be notified that it happened. So watches and notifications is sort of what I'm talking about here. Whenever you start mixing it in with streaming and stuff, there's more and more things you can do with it. But that's at least enough to give you an idea of why you might. But we've not done very much here. It's very simple. We've just extended the length of time that an RPC lasts. And we do notice a couple issues that you should at least be aware of. The first one is load balancing. Load balancing decisions are made on a per RPC basis. So that means that if you have an RPC, at the moment that's created, that you get some load balancing decisions made, but those are going to last for the rest of the lifetime of that RPC. And so if you bring up new backends and you just have a lot of long-lived RPCs, you're like, why aren't any of my backends getting any new traffic? And that is because all of your backends are, all the clients are connected to old backends and they just haven't issued a new RPC yet. The other thing, some people will use max connection age. It's pretty useful for L4 proxies. And max connection age will start shutting down a connection whenever it reaches a certain age. But it by itself does not kill the connection or kill any of the RPCs on that. So it waits for those RPCs to finish. Most of the time they take a couple seconds max, and so everything will sort of clean up. But whenever you start introducing long-lived RPCs, these connections might last for a while. So sort of the pathological case there is each of these old RPCs has their own TCP connection, which if you don't have too many, that's not a big deal. But some people, if you're doing like lots and lots of these, you might start noticing that. The other thing is network failures happen. Like it's network. It happens. Just because gRPC supports long-lived RPCs does not mean you're guaranteed to get 2 months of time for this one RPC. This is your cherished RPC. You never want it to end. So just whenever you're thinking about long-lived RPCs, well, yes, they can happen. You can get quite long time for some of them. Just be aware that you shouldn't assume that you'll always get that amount of time. Things go wrong. Maybe servers are coming up and down. So you should still expect at some points you'll get less than the whole time that you would hope for. And whenever network failures happen, TCP will get TCP connects, and those will kill the calls. We don't migrate from one TCP connection to another or anything like that. The other sort of more interesting thing is network failures. Whenever they happen, you don't know instantly. In fact, if there's no TCP writes, you may not even know because there's exponential backoffs in play. The network itself is unreliable, so it's not just some golden oracle that tells you. So that you need to be careful of. And because these are long-lived RPCs, deadline by its sort of very nature, if you're using that a lot for unary calls, stops being quite as useful for long-lived RPCs. You can still specify it, but it'll be much larger than you would normally have. And it serves less of a purpose than you may be sort of familiar with. So there's a couple different things. I put little asterisks on the ones that basically are the issues that we get to live with. The other things we can maybe do something to combat it, but like network failures happen, yes, I'm sorry, I do not have any solutions to that. But some of the other things we can maybe improve. So for the load balancing, the easiest thing I would suggest is have the server occasionally close the RPC. If you really wish that over a 30-minute period, all your clients were rebalanced, well, go ahead and close the RPCs after 30 minutes. And then that will, over the period, get them all reconnected and let the load balancer make new decisions. And also, I mentioned max connection age before. Well, a sibling configuration is max connection age grace, which is a grace period for how long you let these RPCs last. And so that's just a duration, like if you say 5 minutes, then after the max connection age is triggered, RPCs gets another 5 minutes to complete, and then they'll go ahead and get canceled. So this, even if you don't use it all the time, this setting might still be useful as a backup. Like you still are going to have other mechanisms to close RPCs, but let's say you forgot. This can catch those and kill them anyway. If you're, as far as the network failures, I highly suggest people to turn on client-side keep alive. This is just a setting. What will end up happening is gRPC will end up sending ping frames and cause some network connection, and some network activity. And if we don't get any responses or things like that, we'll go ahead and kill the connection, and you would be notified as the RPC would be canceled. That's really, really, really helpful. And then just while I'm sort of saying things, this doesn't really address anything from the previous slide, but you may find wait for ready to be useful. So wait for ready, I'll say normal RPCs, whenever you issue them, and let's say there's no connection because someone tripped over the wire. Obviously, it's not going to work. You're not going to get connected to the other side. And so those RPCs fail immediately. gRPC knows they're going to fail. You issue the RPC, and gRPC is like, yes, it failed. However, with wait for ready, whenever gRPC knows the RPC would fail immediately because there's no connectivity, like we've been unable to make a connection, the port is closed, or those sorts of things, we'll just not send the RPC. And we'll go ahead and wait, we'll continue retrying to connect and things like that. And then once connectivity is reestablished, the RPC will go out. And so that can sort of reduce the amount of exponential backoff you do manually, or the moment the connection is alive again, the RPC will go out, and so you get actually a little bit reduced latency in those. It's not that big of a deal, but I thought I would just at least give a little plug for it. So that's basically long-lived RPCs. In many ways, they're sort of simple. In some ways, they still impact things. But sort of moving on to streaming RPCs. Streams, by their sort of nature, are just 0 to many messages. Normally, whenever we talk about normal RPCs, we call those unary. Just they have 1. In streaming case, it'll be 0 to many. Each of those messages is ordered, so if you receive a later message, you already received the previous ones. And streaming is independent in each direction. So the ordering is independent, whether or not you have streaming itself is independent. So sort of how that looks is, so we've got client to server. The client would send some method plus some headers and some things like that. It'll send a message and then half close. And so this is just normal unary. This is sort of the normal stuff people are used to. Half close doesn't even normally matter because what's the point? There's only one message. And then the server sort of responds back with some headers of its own. It sends back a message, and then it sends back the status code, which was whether it was okay or not. Hopefully, generally we hope it's okay. So this is just a normal unary. We're going to go really advanced, and streaming is just adding more of those messages. Not too much there. The big thing to notice is the headers and the trailers. That's where metadata goes. So metadata is only at the beginning, at the end of the RPC. You're not going to get those in between the messages. But other than that, it's probably what you would sort of expect. Also, half close becomes more important here because that's an actual signal to the server that it's not going to send any more messages, and you can use that. And so how this ends up looking in the normal sort of protobuf IDL. So I said that streaming is independent. The normal unary RPC is just the normal RPC. You get a single request, you send a single response. Then you can end up doing client streaming. Client streaming, the client sends multiple messages, and then after that, the server does a response. Server streaming, there's a single request initially, and then the server can do as many responses as it wants. And then bidirectional streaming is the last one, where it's streaming in both directions. Bidirectional is a little interesting because it has some emergent properties. Everything but BiDi is what we call half duplex, in that there's only one sender at a time. And even BiDi can be this way, but basically you've got the client send, and then the server responds. And it's sort of always that sort of mix. With BiDi, you've got two streamings going in opposite directions. They can happen at the same time. And so that opens up full duplex. And that's basically gets you something akin to TCP, but instead of it doing raw bytes back and forth, you're going to go ahead and do messages, which can be quite convenient. If you're really familiar with TCP, I'll note that the TCP semantics are a little bit off here because close is different between the two, but a lot of people don't know the full TCP close semantics, so most people are probably not that bothered by it. Because this isn't something even you recognize necessarily, but because there's no longer the client sends, the server responds, you may not realize that gRPC does not provide any implicit acknowledgments to messages that are sent. The only thing that happens is later messages can implicitly acknowledge the messages that came before them. So the normal way this happens is in the sort of unary normal RPC case is there's a request, and then there's the response. And the response implies that the server received the request, because otherwise, how was it generated? And so whenever you start looking at full duplex bidirectional streaming, you need to be aware that just don't assume that because you sent something meant it was received. You need to sort of look at how does each side know that a certain message was received. And so sort of going into the half duplex, and here I'm talking about client streaming, server streaming, and a little bit of the BiDi. I will note though that really whenever we're talking about BiDi, a lot of people get excited about it because it provides full duplex. You can sort of, in some ways, just assume that whenever someone's talking about bidirectional streaming, it's full duplex. But I mean, technically it's not 100% required. So this is a lot of client streaming and server streaming stuff. So streaming itself has lots of use cases. You can use it just for latency or memory reduction. So an example that sort of provides both is sort of like speech-to-text API. So you've got a 1-minute clip. So you're recording, someone's issuing stuff right now, and at the end you would like a transcript of what happened. You can either wait for the full minute to be recorded and then send it, and then the server will process it, and then the response comes. But you could even chunk it up into smaller pieces, let's say 5 seconds or 10 seconds, and you send those as it happens in real time. The server could be processing those as they happen in approximately real time, and then at the last 10-second chunk, the server receives that, processes that, and it's already done most of the processing, and so then it goes ahead and sends back the response with the nice pretty text that knew exactly what you were saying. And so that actually reduced latency because the server didn't need to wait before receiving everything before it was able to do some processing. And it also reduced the overall amount of memory that both the client and the server needed because neither side actually needed the full 1 minute of recording in memory at one particular time. You can also do some you get some little benefits because there's a separation now between the response and the end of the call. Normally with a unary response, the server responds, and now it's given up. Like, not given up, but it has no more opportunity to say anything more about that RPC. With streaming, now you can respond, and then if you want, you can go ahead and respond again, I'm going to bring it up again, but watches are a good, easy use case where you can see how this could be useful. You can say, I'm interested in some topic, and it can tell you, oh, hey, here's what's happened on that topic. And then if something else happens, it can go ahead and send that to you immediately. You don't need to wait for any RPC to request more information. And that can reduce latency and just reduce the amount of churn of the RPCs. Another nice benefit of streaming is you get flow control or pushback. This is where if a sender is sending faster than the receiver can consume it, it'll go ahead and slow down the sender to whatever the rate the receiver can process it. And this can be really useful for like bulk uploads. So normally whenever you upload, you need to do chunks. And so you upload a chunk, you wait for the response. Okay, that one's good. You then go ahead and send another chunk, and you wait for the response, that one's good. Each time that you wait, that's latency, that was lost bandwidth that you could have had. Instead, you can actually send one after the other in the stream. If you're sending too fast, you'll be slowed down to whatever the network can handle. And so you don't end up having to incur those delays where you end up waiting at the end. And so that can save, that means you don't need to tune the chunk size as much. Like you don't want 1 byte, but you also don't want 1 gig. But anything sort of in a medium range will do pretty reasonably well. Whereas before, with the sort of chunked and then you wait, you're sort of encouraged to have really large chunk sizes so that those wait times, if you're on a high latency link or things like that, they don't occur as much. They're not as big of a penalty. And basically, some of this is just pipelining, if you've heard about that in other situations. Streaming just gives you pipelining. Streaming, because you've got all these messages, they're ordered, they've got implicit state. You can associate state between these different messages. So some simple things with that is all these RPC messages are going to the same backend. The stream is tied to the backend, and so you know the same backend is receiving everything. It knows about the things that came before, and you can use that to your advantage. Also, the call lifetime itself has been expanded. Before, it was only the request and the response. Now you can do a lot more things within the call. So for example, if you want to have a transaction where you end up sending multiple requests, which are each a query or an update or things like that, you can either use the call lifetime itself for managing the transaction or so if the call gets killed, the transaction gets killed. But you now have this new larger scoped thing of this lifetime of a thing that you didn't have before, which is the RPC lifetime itself, and not just an individual message. You can also reduce the per message setup costs. So like the watches I was talking about before, you don't have to tear everything down. And so you can just, the server already knows what you're wanting. You don't have to just artificially create new RPCs just because that's how the system has to work. And then one sort of interesting thing is because all the messages are ordered, you can actually provide a full state at the very beginning, and then any just deltas of changes that are happening after that point. And that can be really useful. Watches, again, are pretty easy. But the sort of deltas and things like that, you end up having to do quite a lot of infrastructure if you want to do that in normal RPCs, in unary RPCs. You're going to have some tokens or recovery token. So what was the previous state you saw? But in this case, the server can just say, here's the current state, and then as changes happen, you send it out. And so there's much less synchronization between the client and the server, and protocol is sort of simpler. But there's complexities, there's issues. With streaming and a lot of this, it's not for free. There's complexities involved. So make sure you're getting something out of the streaming or the long-lived RPCs. Don't do it just because, well, gRPC provides streaming. Obviously, I want to use it because it's the greatest feature in the world. Unary RPCs, I'm not trying to burn them at all. They're actually really great. Most RPCs should be unary RPCs. But as we talk about through all these issues, keep that in mind that, make sure that what you're getting out of these advanced features are actually benefiting you more than some of the issues you now get to deal with. One thing to be aware of is that gRPC has flow control. I mentioned that for the streams, but that has very large buffers relative to what some people may consider large in certain circumstances. So we see some streaming RPCs that have messages that are 5 bytes large. Well, 64K seems really, really large whenever you're talking about 5-byte messages. And the flow control is point-to-point. So if you add new nodes into the middle with new, let's say you've got a new proxy, that's going to be an L7 proxy in the middle, it can add its own buffers. And so you can very easily be looking at megabytes of buffers. That'll vary depending on your network and some of the actual concrete implementations, but just be aware that it could be large. And I already mentioned the API complexity. It's both the complexity of the system itself. It can do more. That means you need to be aware of more cases before it's real simple. But also the APIs themselves in the languages. We have optimized we do think that most RPCs are unary. Those are the ones that we try to make as easy as possible. Streaming is a more advanced use case, and so it's intended for you to be able to get some of that power. But it also means that you incur some complexity, and that'll vary a little bit per language that you're sort of interacting with, but be aware. Whenever you're doing streaming, very often your normal retries, like if you've got sort of a framework level retry, it stops making as much sense. So you may end up, especially with server streaming, you may end up having trouble and needing to implement a retry inside the application itself, as opposed to any sort of framework level, something that's automatically doing it. And that's because you're going to need to have some specialized logic in order to retrieve just the new things that you wanted and not have to reissue the full RPC. So just be aware of that, because it can be a little saddening whenever you realize that. And tracing and stats systems are not necessarily all universally expecting streaming, and so it can maybe get muddled a little bit, or it might be missing. That'll vary per system, and I don't know all of the systems out there on how well they do here, but be aware that it may be a little harder to investigate what's happening in the system. So the things that we can actually control there is if there's flow control problems. I mentioned the large buffer sizes. If that's a problem for you, then I suggest you actually go full BiDi, full duplex. And what that allows is you can end up doing application level flow control. And what that is you end up having little messages that you send on as part of your streams that say, go ahead and give me 2 more messages, or go ahead and give me 2 more events, or go ahead and give me 2 more jobs. So that you request that in a normal message, and then the other side, like the server, can go ahead and give you 2 more jobs. And that way it's not queuing up at all within gRPC. You're sort of preventing the remote side from sending it in the first place. And the benefit of that is that's also end-to-end. There's some complexities there in that at times you have to decide how many do you want to be outstanding at a time. You get to tune that. But to get that sort of features, those are the things you need to do. Tracing stats for especially half duplex streaming. A lot of times if you sort of treat it just like unary, you're like, oh, okay, there were 5 messages, but let's just claim they were for 1 really big message. It'll mostly work out. Depending on what you're doing, like some of the watches and stuff, it may not work out as well. But in plenty of cases, it will to be a pretty close approximation. And so you may not be that bad off. But now we're getting into full duplex streaming. This is the really advanced stuff. This was supposed to be an intermediate talk. A lot of the streaming you can do intermediate pretty well. At the end of doing a full bidirectional protocol, I would consider you advanced. That is the advanced stuff we're doing with gRPC. And that's because you basically have TCP with messages. You can sort of do whatever you want. So whenever you can do whatever you want, you can do whatever you want, and you then can potentially be your own worst enemy. But you can make any custom protocols. You have a full escape hatch to do whatever you need. And as I mentioned before, you've got application level flow control, where you can explicitly request which things you're going to want to not necessarily rely on the gRPC flow control. Transactions can work pretty nicely here because you can actually be issuing requests or queries and then receive the response for the queries, and that all happens in conjunction on these streams. And then if, let's say, the client dies, it crashes, the RPC itself will get canceled on the server, and so the server knows to cancel the cancel the transaction. You can sort of do a couple sort of fancy things around those. You can also do live reconfiguration. Since things are all, you've got the organized state, one message follows the other, you can say, oh, I'm interested in 5 different topics for my watch. And then later you're like, oh, actually a 6th one would be great too. And a little bit later you're like, get rid of that 3rd one. And you can change it on the fly. And you're not needing to tear down the old one, bring up a new one, and figure out what do you do in the middle point because there's a race or anything like that. And you can also do bulk uploads. So before I mentioned bulk downloads for just the half duplex case. The reason uploads are different is because you really need resumption, typically with large bulk uploads. And that means as you're uploading, you need resumption keys to come back to you. And so in that case, the client would remember the last resumption key that it received. If something goes wrong, it will go ahead and create a new RPC and just resume based on that key. This still has some benefits though, because you're not having to use that key continually. So normally, if you're doing bulk uploads, you're using the keys constantly. It's a very normal, common case. In this case, with the bulk uploads with streaming, you sort of delegated it to, it happens, but it's not happening constantly. It doesn't need to be quite as optimized as normal. And then sort of off to the side, there's the half close that I mentioned sort of came into the picture before. And you can go ahead and use that to sort of cleanly hang up and tell the server you're not going to send anymore. And that can sort of let things close gracefully. So full duplex, we get a couple more issues. Stats tracing systems may be overly simplistic. That looks a little bit similar. It becomes a bigger problem with full duplex. We have API protocol complexity. You are dealing with 2 streams that independent events are happening on. That's complex. Like like we talk about threading and things like that, your code itself will become more complex because you're doing something more complex. And I would not underestimate how much impact that can have. At this point, you're almost guaranteed to have application level retry. It's really, really hard to avoid. Any retry system doesn't really know what's going on. And so you're going to have to do it yourself. There's flow control, there's pushback, there's all these things. That means you actually open yourself up to deadlocking. Yes, your RPCs can deadlock. Beware. That's not something that you might think about. So just beware, be conscious, because you can go and do all these other RPCs for so long and not have to think about that. And if you do full BiDi, then or full duplex, then basically REST conversion is thrown out. There's really no hope for that, given the REST ecosystem. So a lot of those we couldn't do very much about, but as far as the deadlocks, the best way to handle that is make sure that at any point in time, at least one side is receiving. If you do that, then everything sort of can flow through the system and it'll be okay. But if you ever get to a point where both sides are sending and nobody's receiving, that is a potential for deadlock. Also note, just because you tested it once and it didn't deadlock doesn't mean anything. I mentioned there were buffers in the system. Those can change based on live network behavior. And so maybe you had 1 megabyte buffer whenever you tested, and it's been like that for a while, and then the buffer sort of diminished and it became 64K. And that would be enough for a lot of people to maybe notice the deadlock in that case, but it didn't happen before. And so now let's go ahead and plug the 2 together, long-lived plus streaming. We had load balancing before. Before it was mainly CPU was the issue for load balancing. That's because they wasn't doing very much. It was a single request, single response. It's just sitting there waiting for something to happen most likely. It wasn't CPU before, it was memory before. It's just sort of sitting there consuming some resources, but probably not too active on the server. Now we're talking about streaming. There's lots of stuff happening all the time, but we're talking about the transaction case, for instance. All these messages are implying quite a lot of load. And so you have both memory and CPU now. So the moment you're doing long-lived streaming RPCs, definitely watch out for load balancing. Before, with just the long-lived RPCs, load balancing comes into play, but it's not as dire. And then again, tracing and stat systems may be overly simplistic. Before, I said that if you're doing streaming, it's mostly fine because you can just sort of assume all the messages are one big message. Here, we're spreading out the messages over time. It's really, really spread out. And so that sort of extra delays become very noticeable and make it much harder to debug if you don't see those in your step systems. But really, as far as solving the load balancing issue, it's going to be a lot like what I had said before with the long-lived RPCs. Nothing really changes. Occasionally, you should go ahead and clean up RPCs, let them go ahead and finish, let them go ahead and pick another load balancer. But that's going to be basically it. And so then that's what we've got. I'm very eager for Q&A. If I've got my email and Jitter up there, sorry, GitHub, I'm on Gitter as well. If you send me any emails, please send a link to gRPC.io as well. That's the mailing list because there's lots of people who can answer stuff. And then shameless plug that gRPC at Google is hiring. You can come talk to me and I'll get you some contact information. Any questions?
You didn't talk about, there is an option of max concurrent streams, which is defined, as if I remember, by default to 100, which is quite low. Do you have any recommendation regarding that and how high we could go of multiple streams between a lot of clients and one server application?
Yes, I should have mentioned that, although honestly it can apply it in many different cases, not just, I guess that mainly impacts long-lived RPCs. And so there is a configuration setting max concurrent streams that comes from the HTTP 2 spec. gRPC has it as infinite right now for all of our main implementations, but lots of proxies will go ahead and choose something less than that. And so like if you're using some services with some Google API services, you might see 100. 100 is pretty common as it's specified as it would be, how does the spec put it? Basically, it should not be something less than 100 or something sort of wishy-washy like that. And so a lot of proxies want something really small, and so they chose 100. Yes, anytime you're doing lots of concurrent RPCs, and especially long-lived, if you're doing something on the order of hundreds or thousands of these, you could run into that problem. And then the requirement is that you open up multiple channels or get gRPC to open up multiple connections. So the question is, if the flow control is back pressure handling, is it something automatic or is it, do you have to manage it? That'll vary per language. It's sort of an API feature of how does that get exposed. So if it's a blocking API, it's going to totally just be, it's going to slow you down by blocking. Some of the async APIs have you can only have one outstanding message. So until it tells you it is process that message, you can't send another one. That is another form of it. In Java specifically, it's advisory. So the idea was that if you already have a message, might as well tell gRPC about it, so we're not going to get too upset. But if you're not watching the flow control, and if you're not looking at, say, if you don't ask gRPC, hey, are you ready for more? Then you'll just end up buffering a lot locally. But it'll bubble up differently in each language. So that does, you do need to look into that, but it'll vary. Yeah, any other question?
What tools do you use to debug on the wire when you're trying to find these issues with gRPC?
The question was about how do you debug on the wire?
Yeah, I can't use Fiddler anymore. So like what sort of things do you use to debug?
In general or streaming or long-lived specifically?
I would say long-lived streaming, complex cases.
I think in general, I wouldn't do it as much on the wire level. I would look more at the events that are coming higher in which messages are being received. A lot of stuff can happen on the wire, and you don't necessarily need to be an HTTP2 expert to follow along. If you get that deadlock issue, then that is something you could look at and like, oh, the window size is different in this case versus that case. There are some debug flags you can put in to see all the HTTP2 frames. Unfortunately, that'll vary per language. So at times you can do that. Generally, I try to avoid needing to suggest someone to do that because that's quite involved. But I think commonly just at the gRPC layer, what the APIs provide, if you just log that yourself, or turn on the frame logging and you sort of ignore a lot of the HTTP2 stuff, you can get pretty far. But tracing and stats are also great, or tracing is also pretty good for that. Yes.
Hi, my question is related to if you have a service somewhere and you can't invoke a normal unary RPC to it, like let's say it's behind a NAT and you can't punch a hole through that NAT, is using a streaming RPC an acceptable pattern that you've seen used for getting around that sort of thing so that you can listen for requests in the opposite direction?
This is really you mentioned listening to requests in the opposite direction. That's a use case that comes up pretty frequently. It's not everyone having to deal with it, but whenever you're needing to deal with it, you're really needing to deal with it. And so this is basically the core problem is the client and server are reversed. Who's requesting who to do what? The client can't access the real client can't access the real server, and so you sort of have to do some hole punching. Yes, you can totally use streaming for that. That turns out to be typically BiDi, full duplex streaming, which is the more complex case I was mentioning. But yes, that is totally something that is totally a use case to do full bidirectional streaming.
Do you foresee any type of updates to gRPC in the future where that sort of use case is abstracted away so you don't have to actually deal with a streaming RPC and you can define it as a unary RPC? So I have a proof of concept PR for Java. I know it's easy to do in Go as well. I worked on it a little bit. There was this idea of basically making a reverse tunnel. We would have one RPC that would be full duplex BiDi, and then we end up just using that as a carrier for a bunch of bytes. And then it ends up layering HTTP2 and gRPC on top of that. And that gets you a pretty good inversion. I ran out of some time, and so that stalled a little bit. But I think there's a issue open for that it receives a reasonable amount of pings because I requested people to ping it. So there has been some look at that. It's totally feasible, and I've got a proof of concept that totally works. The question is more just protocol details of what we're going to do there. There's a couple decisions to make. And that's something that would be helpful to have a little bit of community involvement with because you basically need the client to register with the server and exactly what information it provides, how fancy or simple is that. That's most of where the remaining design questions are. Thank you.
Mm-hmm.
Okay, only one more question.
Hi, is the streaming and long-lived operations supported in all the language bindings?
Yes, the streaming and long-lived RPCs are supported in all the clients. It is something though that whenever you start using gRPC web, those sorts of things that you may not get. So for example, BiDi, you don't get full BiDi, full duplex streaming in gRPC web. But all the I'll say native implementations, so the main 9, they support all this.
Thanks.